Hello, my name is Philip Enriquez, and this is my lab 4 for Physics 2211 about oscillations. So for this lab, we're going to start with an introduction for the lab, then we'll have the theory and the main formulas behind the lab, then I'll present the tracker model I did, then the glow strip model I did, and finally end with what does it mean, with part 1 and part 2, that will make a comparative analysis between the two models. In this lab, we're going to analyze the motion of a mass on an oscillating spring using tracker, and then we're going to construct a model of this motion using glow script, a predicted model, and then we're going to end off the lab with what does it mean, that will establish a comparative analysis between the predicted and observed motion of the mass. For this lab, we're going to once again apply the principles of Newton's second law with this formula right here. We're also applying Hooke's law with the formula stated right here, the energy principle stated right here, taking into account potential gravitational energy stated right here at the surface of the Earth, taking into account also potential spring energy stated right here, and finally potential kinetic energy with the formula stated right here. And then for the calculation of the K constant, we're deriving from this formula, the time oscillation formula, and we derived it like this for the K constant. And then for the calculation of LO that we're going to do later on in the lab, we are using this formula right here. This right here is a video I edited with Tracker. We can see right here how Tracker is constantly plotting data of the position of the X and Y values of the mass attached to the spring that is oscillating. And we can see that one oscillation in X goes from this point to this point, and one oscillation in Y goes from this point to this point. These values of time of oscillation is something we're going to use later on in the What Does This Mean part 2 of this lab. Now we can see the computational model for our motion. In glow script, I enter the initial position, velocity, and the mass of the object stated right here. We can see that the initial velocity is 0 and the initial position is given by the previous graph. Then we calculated initial energies right here, and then we use the net force as a sum of F grav and F spring right here. After that, we calculated the changes in velocity with Newton's second law, the changes in velocity and position, and then we finally calculated the changes in energy over here with the energy principle. And this is how the computational model actually ran. So we can see right here what the model looks like. And now we're going to compare both models. In the first two graphs, we can see the position in X and Y versus time in both models. The blue curve is a predicted motion from our computational model, and the red curve plots the values that we got out of Tracker. There's a small discrepancy between the graphs. This occurred because of two main things. The first is that we're not accounting for the drag force in the computational model, and also the frames of the video didn't reflect exactly the motion. So in order to better this, we could have taken into account drag force with more, that would take more computations. And also, we could have done a higher quality and higher frames per second video that would have given a more precise value. We finally asked if the energy principle was satisfied. We can see that it is satisfied, as if work equals 0, it means that the total change in energy is 0. And in the third graph, it is reflected with the orange line, and we can see that the orange line is plotted at 0. So the change in energy is equal to 0, which satisfies the energy principle. Now finally, to estimate the period of oscillations, we used the graph made by Tracker and recorded the time per oscillation by looking at the values right here in each oscillation and the time in each oscillation. Then we used this period to estimate the spring constant using this formula, and we can see there is a difference between the two oscillation periods in X and Y, and therefore there's a discrepancy in spring constants. In order to get a more accurate estimate, we could have used the average of all oscillation periods in X and Y instead of calculating them separately, and therefore we could have gotten a more accurate estimate to the spring constant. Well, I hope you really enjoyed this lab and learned a lot, and thank you.